So in the previous lecture, we discussed breakthrough analysis, right, or the dynamic response in a packed bed column. So we said that there are two ways of doing the experiments on adsorptions or test on adsorptions. One is the batch and one is the flow. Today we begin with stage-wise operations. So we have adsorption, and we are looking at stage-wise operation. Okay. So in stage-wise operations, essentially we have some container where you bring, say, the solvent, LS if you call it, or you have solutions. It contains certain amount of solute. So let's say LS is solute free basis. So solvent you have, say, kg per second. You can also have a batch operation. That means we are talking in terms of how many times. So we can work on kg per second, or we can just work in kg. So it's a question of choosing a proper basis here. So you have solvent, and say the mole fraction is Y0 kg of solute per kg of solvent. Okay, so this solute could be, say, organics, say color, or certain dissolved organics in water. Okay, so now you bring in contact with some solid. So let's say the solid is flow rate is SS. Now this is also again kg per second, or if you're doing in some batch, so you can have the basis of kg as well. Now this adsorbents could be fresh. So let's say if the solid concentration in the solid phase is x1, so we have kg of color or the solute per kg of, say, solid. So again we are defining solute free basis. Okay, so this is x1 here. This could be 0, very small quantities. So you bring essentially a solvent adsorbate. Okay, so adsorbate will be this solute dissolved in this aqueous phase, some liquid here. You bring in contact with adsorbent. Adsorbent may be fresh or may contains very small amount of this solute. Then you bring in contact, and finally you withdrawing this treated solvent or feed. And here also you can have, say, this is LS. So LS will remain the same because you are working on solute free basis. So assume that the solvent is not getting adsorbed on this solid. So let's say you have charcoal or you have carbon. So in principle some water will also get adsorbed here, but let's assume that LS remains same here. Now this LS will also have certain units. So you have Y1, which is also kg solute per kg of solvent. And now this adsorbent will pick up the solute. So here you have the flow rate as SS. So again, it's the solid free basis. Amount of adsorbent will remain the same, and this will have a concentrations. Let's say we call it here, if we call it x0, let's say this is x1. So x1 will be kg solute per kg of solid. All right. So notice this nomenclature here as given the textbook x1 or x0, but essentially this is nothing but what we have used earlier also, Q, uptake. All right. So how much amount of milligram per gram is the most common unit. So how much milligram of solute has been adsorbed per gram of adsorbent. So that's the most common unit used here. We are of course using here kg per kg. Okay, and here if we talk of the isotherms, so then you have here you have C, or partial pressure of the solute in the gas phase. So this C would be milligram of solute per liter of solutions. Here this you have partial pressure, say, atmosphere. You can also work on the mole fractions in the gas phase. So given fixed T, you have this isotherms available. So much of C, you have Q. So instead of working on this C and Q, In this problem, let's say we are working on x and y. So these are all solid free bases. You know the advantage we have said earlier also. The operating line based on the solid free mole fractions, they remain linear, they remain constant. So that's the advantage working on this. So let's come back to this. We have brought this adsorbate in contact with the adsorbent. We have the treated feed and we have the spent solid. So this is your spent solid. So charcoal has picked up certain amount of solid here. So if you make a material balance or a species balance, you have Ls y0 minus y1. So the concentrations has been brought down from y0 to y1 by this charcoal which has picked up. So let's say this SS is a flow rate kg. It has picked up char color or whatever organics you have as a present as a contaminant, x1 minus x0. All right. So essentially, if you want to plot on this y versus x graph, so this will be your, let's say, equilibrium curve. So all we have done, we have converted the q versus c, right, in terms of y versus x. So this is kg of solute per kg of solvent. So we are plotting like this, y, and x is kg of solute per kg of solid. All right. So we have only one stage, let's say. So we start with some y0. So that's a concentration in the liquid phase or the gas phase, very large amount of y0, and you have brought in contact with a very nearly pure adsorbents, which does not contain any color or any solutes here. In principle, there will be very small amount here. Okay. So if you look at the balance equation which we had, Ls y0, say minus y equals Ss, and you have x minus x0. So y equal to mx plus c. You can make a notice that the slope will be negative. So this is operating line equations. This would be minus Ss by Ls, the slope of this curve. So the concentration of this liquid phase will decrease and the solid phase concentration will increase in these directions till we hit the equilibrium. So if you have the ideal stages and we are assuming that the two streams have spent enough time, then the spent solid and the treated feed will have concentrations which are in equilibrium or given by this equilibrium curve. So essentially we have come down to x1, that's the lowest you can come down, or that's the lowest, that's the maximum you can increase solid phase concentrations, uptake, and the lowest you can come down is y1. So y0 to y1 and x0 to x1 here. Okay. So essentially what we are saying here again, that all these isotherms which we used as q equal to kc to the power 1 over n, if you talk of Friendly's isotherms, so we said that is the most common isotherm from engineering point of view, where we relate q in terms of c. This can be converted into y equal to m x to the power n. So from thermodynamics, classically we have obtained, we have some certain data which we did from the batch experiment or the column experiment. We fitted with this line, we got the equation q equal to kc to the power 1 over n. We have converted into y equal to mx to the power n, so that we can plot operating line equations on the same plot. An operating line is a straight line because we are working on the solute free basis. Solute free basis. All right. So coming back to these equations, now you can write Ss over Ls. So how much amount of charcoals or adsorbents is required per amount of solvent. This should be, this is equal to y0 minus y1, and here you have x1 minus x0, but let's say x0 is very small amount, very zero. Your fresh adsorbents, okay, or this amount is much larger than x0. In reality, as you said, you take the spent solid and regenerate and bring it back to the adsorber, okay, but in that process there will be some amount of solute there, but the solute will be much smaller than your these concentrations, spent solid concentrations. So now you can write as y0 minus y1, and if the stage is ideal or you have given enough time, then y1 you can write as m into x1 to the power n. Essentially this line, this coordinates of y1 x1, they lie on this equilibrium curve. So we can replace here x1 with y1 over m to the power 1 over n. So this would be the most simplest or the basic equation for one stage adsorptions. So let's go back to this equation. What is given? We have been given a feed which concentration is y0. We have been asked to bring down this concentration of say color from y0 to y1. We have been given the amount of this liquid is Ls. To do this, we are bringing in contact with some charcoal, Ss. Question is how much amount of charcoal is required. This charcoal is fresh, x0 is 0. After adsorptions, this concentration will increase, liquid phase will decrease, solid will increase to x1. But we are not that much interested in knowing this, how much is the amount of x1 here. So that's why we have replaced x1 in terms of y1 and other parameters, the properties of this isotherms, slope of the curve and the power index here. So y1 is known, y0 is known, m, n, they come from this equilibrium curve equations. We can find out this ratios of Ss over Lss per 1000 kg of liquid, how much amount of solid is required from here. Okay. Now look at the slope of the equilibrium curve. We have y versus x, and here we have m as a slope and n is the power of index. Now if n can assume different values, that means when you plot y versus x, isothermal may be like this. So when you plot like this, or if you obtain your data like this, all it means n is greater than 1 and you have a very favorable isotherm, because this gives a very large capacity, very large amount of y can be removed by this solid. Look at the slope of the curve, it's monotonically increasing, very fast rising curve. That means if you start with y0, it's a certain x0, slope of the curve is like this, which is minus Ls minus Ss over Ls. Now n is 1, that means you have y1 equal to mx1, straight line, you will have the slope like this, straight line, and this is n equal to 1. Generally n equal to 1 to 2, it's known as moderately difficult separation or adsorptions. So n is greater than 1, everybody favors larger values of n, the curve will be more and more increasing, very sharp rise here. N equal to 1, in that case the slope or the operating line will be a straight line, except it will end here. Similarly we can have n less than 1, so this is n less than 1, and it says it's a very poor adsorptions. It's very difficult to remove from the solvent phase, because look at the slope here keeps on decreasing here. In this case, of course, you will have the slope like this. So we have three cases depending upon type of isotherms: y versus x, n greater than 1, n equal to 1, n less than 1. N greater than 1, it's a favorable isotherms, it's very moderately difficult. Look at the slope, Ss by Ls, here also is minus Ss by Ls, here also minus Ss by Ls. For the same amount of Ls, you can see from here you require a very large amount of solids. Now we take multi-stage, so this is your single stage here. Now let's take, if we have multi-stage cross current adsorption. Okay, so you have stage 1, we have stage 2, LS Y0, SS1 first stage, this is X0 here, spent solid is concentration is X1, this is now your Y1, again bring in contact with the solid SS2, say you have X0 here, same concentration of charcoals, fresh adsorbents, and after treatment SS2, and here you have X2, and the treated solvent is Y2. Flow rate LS will remain the same throughout, okay, because all you have solid free bases, so LS is same here. Similarly SS1 is the same here, SS2 and SS2 they remain unchanged, only the mole fraction changes. We are working on the solid free bases. Again for the stage 1 you can write a balance here, Y0 minus Y1 equal to SS1 X1 minus X0, let's say it's 0 for simplicity, so fresh adsorbents. This equation you can write SS1, how much amount of solid is required in stage 1 over the amount of solvent treated, will be equal to Y0 minus Y1 over X1, but X1 you can write as Y1 over M to the power 1 over N. So Y1 X1 they are in equilibrium, Y2 X2 they are in equilibrium. Okay. Similarly we can write down this balance for the second equations. Second stage we have SS2 over LS, this would be equal to Y1 minus Y2 over X2, but X2 we can write as Y2 over M to the power 1 over N. So what we want to do here, we may like to optimize total amount of solid, SS equal to SS1 plus SS2. How much is the total amount of solid? Should we use a larger amount here or should we use a smaller amount here? Okay, so if you add the two amounts here, one can write SS1 plus SS2 over LS. Alright, this will be equal to, if you add these two and rearrange, one can show that you will get M to the power 1 over N, Y0 minus Y1 over Y1 to the power 1 over N, plus you have Y1 minus Y2 over Y2 to the power 1 over N. Okay, so one can optimize total amount of solid is now SS over LS. How do we optimize? LS is fixed here, Y0 is fixed, Y1 is fixed, sorry excuse me, Y2 is fixed, N is fixed, M is fixed. So intermediate is your Y1. Alright, so all it means, what is the total? First stage should we use equal amount, 50% of SS, or should we have 40-60 or 60-40? That will decide what happens to this intermediate concentration. So essentially one can differentiate mathematically D of SS over D of Y1. Y1 is intermediate. We can differentiate these equations to obtain an expressions for Y1 in terms of the known quantities. Okay, before that let's plot graphically what we're trying to do here. So we have this X, Y equilibrium curve here. Let's say we are using N greater than 1, favorable isotherms. Okay, Y0 is fixed. Let's say X0 is 0. So fresh adsorbents. If we know the amount of solid in the stage 1, we can take that operating line and we can reach this intermediate concentrations Y1. So this would be Y1, this would be X1. Alright, this will be the slope of the curve as minus SS1 over LS. So if we know this SS1, yes, we can draw this operating line. This will intermediate concentration will be fixed at Y1. Okay, unfortunately we don't know. Let's assume that if this Y1 is known, then from here now I go to the second stage, take a different slope, minus SS2 over LS to come down to this desired level of Y2, for which we have this x2. So I can go back to the previous question we had. Y0 is fixed, Y2 is fixed. We have been asked to reduce these concentrations. X0 is fixed here. Alright. So these three quantities are known here. N is known, slope of the curve M is also known to us. Okay. We want to know how much is the amount of total amount of solids. SS equals SS1 plus SS2 equal to what? Alright, so that's what we said, that this Y1 is an intermediate quantity. If you fix any of these variables, suppose you fix Y1, you can go back to this, you can draw this line, then we can calculate from the slope how much is the amount of the solid required. Once we know Y1, we know Y2. Okay, from here again Y2 and X2, they are in equilibrium. The last stage, we fix this point, you connect this, you get SS2 here. Alright, so any of these three quantities, Y1, SS1 or SS2, if we know, we can complete this discussion here. Mathematically, we go back to this, differentiate this equation, SS1 plus SS2 over LS over dy1 equal to, and set to 0. Do this as an exercise to obtain an expressions for y1, intermediate, this quantity here, over y2, 1 over n minus 1 over n, y0, y1 equal to 1 minus 1 over n. Solve for y1. Once you know for solve for y1, you can calculate all SS1, SS2, x2, x1, everything. So both either graphically, alright, or by this differential equations, one can solve to optimize how much is the minimum amount of SS min required, what combinations actually, which will give you desired, not the minimum amount, the desired amount of solid, so that we obtain this Y2 concentrations. And actually when you solve this, of course it looks like there's an iteration here, Y0 is fixed, Y2 is here, so one is to solve this by trial and error or some numerical technique to obtain these values of Y1. Then you can go back and put the equation for the first stage and the second stage to obtain the other quantities. In some of the textbook, they have also reported the solutions of y1 over y0 for different values of n. For example, Trebol reports a graph very similar to this, 0 to 1, 0 to 1. There you have different type of curve here for different values of n. So n equal to, let's say, 10, very large, very high favorable, to very small amount of n, 0.2, which is non-favorable. So for everything they are reported here, some log plot. From this also one can calculate this y1. Okay, so either graphically or already available plot like this, or by mathematically one can solve for this cross current multi-stage adsorptions. Okay, we begin with the next topic, which is countercurrent multi-stage operation. Okay, here also, so far in the cross current, we will have some certain examples in the next class to address how much amount of solvent is required to bring down this level from, say, y0 to y1. Okay, or given the number of stages, what is the final concentrations in the treated feed, or how much is the amount of uptake here. All those we will take the example in the next class. Okay, so let's continue with this countercurrent multi-stage operations. Okay, so which is also very similar to what we had in case of extractions. So we have stages like this, say stage 1, stage 2, and the last stage NP. So you have solid, or you have, say, solvent LS. Essentially you have feed, but again you want to work on solid free basis. So it's kg per second. Mole fraction is y0. Free solid free basis, kg of color or kg of adsorbate per kg of solvent. and then you have nomenclatures y1, you have say y2, you can have a break here, the last is np, so this would be ynp minus 1, and the treated feed will have the compositions mole fraction ynp. So this is your final solution or final solvent. And to do this, you have brought SS adsorbent. This concentration is xnp plus 1, which could be 0 phase adsorbents or approximately 0. So we have this xnp, stage 2, this would be x3, stage 1, this would be x2, and finally the exit concentration mole fraction is x1. Okay, and we can always ask several questions like how many stages are required, different type of questions, how many stages are required given this ls, given this ss, from this level to this level, or the question can be asked amount of adsorbent. So one is to look at the degree of freedom, what is given, what is not given, or given this number of stages, amount of adsorbent, what is the final concentrations one can achieve in the treated solvent. So different questions can be phrased or rephrased in different manners. Okay. Now how do we do this? So we have the similar treatment. First is of course one has to make an overall balance, overall material balance or overall species balance. So there you have ls y0 minus ynp equals ss x1 minus x np plus 1. So this overall material balance, and from this one can obtain ss by ls in expressions in terms of the 4 boundary mole fractions x1 minus xnp plus 1. Alright, we can plot or we can explain graphically again y versus x. Let's say we have this equilibrium curve like this, we have now the operating line. So what is the operating line? This connects your bulk phase concentrations ynp x1 or xnp plus 1. Okay, so starting from overall balance, if here this is y0, so we are talking of now stages 1, 2, and at the end we have x or np. So y0, which is here, and we have x1 here. So two phase concentration, two streams y0, and now we have this x1. We bring down to the level of, so this x1 here. Now the last here you have xnp plus 1, which could be very small. Let's say this is xnp plus 1. So what you will obtain here, it will be this ynp. So that's the meaning of this operating line equation, the material balance ynp. And then you have all these stages. We assume that x1 equilibrium with y1, so go to this x1, you have this now y1. Once we know y1, then from the operating line we can get x2. So this is x2. Alright, and so forth. Once we know x2, we can further construct to obtain this on different stages, stage 1 and stage 2, etc. And if you recall, now in the beginning we said in the class on absorptions, or wherever you have this countercurrent stage processes, there is a risk of pinch, right? All it means operating line, wherever it intersects, there will be pinch, mass transfer will be 0, and we require infinite number of stages. So from here, of course, this will give how much amount of solid is required, SS over LS, but one has to also determine the minimum amount of adsorbent. Alright, so it's all we have to do is redraw this curve, say let's say y versus x, and the treatment is same. We have been given y0, we know the last stage ynp, corresponding to which we have solid phase concentration x and p plus 1, which could be very small or very zero here. And now to find the minimum amount of adsorbent, we connect this, so that's a line, straight line, which will give us zero driving force here. We can obtain SS over LS, minimum amount of solvent. From this we can obtain, then we can have the operating SS over LS, let's say 1.2 or 1.5 times the minimum amount. So we can construct this to obtain the spin concentrations of the first stage, which is x1 here. And then we can reconstruct the different number of stages required once we know this operating line and once we know this equilibrium curve here. Again, here one has to be careful with the shape of this isotherm. Let's say if we have isotherms like concave downward, then this is y0, and let's say this is very small amount here, x and p plus 1, and we are treating this fluid or this feed till y and p. If we draw this line here, then this SS over LS, of course this will give us some amount of SS, amount of adsorbent required, but then you have to be careful that there is a possibility of things becoming tangent. That means you take this point and find the tangent, or wherever it crosses, it touches this point here. That means one is supposed to calculate this slope here. This slope will give us the minimum amount of adsorbent required. So this is also very similar to the in case of absorption, when we had different type of solubility curve. Then you get this x1, which will give you the maximum concentration of your spent solid. All right. So whether you have concave downward or concave upward, one has to do some inspection to see the curve and see where it makes a tangent here. Okay. Now we move on to this and see how we can apply this Freundlich isotherm equations. So what we will do now, we'll set up the equations, and so we have two stages for simplicity, stage 1, and let's say we have stage 2, and we have this counter current operation. So y0, we have x1, this is y1, y2, here we have x3, which is nearly 0, this is x2 here. Amount of this adsorbent remains the same as SS, solid free basis, and the amount of solvent here is a fixed, which is your LS. Okay. So let's write down the expressions. Overall, of course, we can make a balance, say SS x1 minus x3, which is 0, LS y0 minus y2. So whatever is lost here is picked up in this solid as an uptake. But x1, notice, and y1, they are in equilibrium. Okay. So let's write down x1 as y1 over m to the power 1 over n. Similarly, we can write down for the third stage, for the second stage, as SS over LS equal to y0 minus y2. So what we are writing right now is same equations. If we substitute x1, let's say in terms of y1 in this equations, and then we can write SS over LS as y0 minus y2 over x1, which is y1 over m to the power 1 over n. Okay, so equation 1 is operating line, equation 2 equilibrium curve, the two together has given us these equations. The ratios of SS over LS, y0, y2, they are known to us, y1 over m to the power 1 over n. This y1 is not known, this is intermediate concentrations. Okay. Similarly, if you write down the balance for the, let's say, the second stage, then you will have LS y1 minus y2 equal to SS x2 minus x3, but x3 is again 0. So we have done the overall balance, and now we are writing this balance for the second stage. Okay. So here we can write SSX2, again x2 we can write in terms of y2 over m to the power 1 over n. So x2 is in equilibrium with y2. So all we have done, we have replaced solid phase concentration x1 and x2 in terms of corresponding y1 and y2. So we have this second independent equations, the two together. Again you have ls and you have ss. Here also we have ss and lss. One can substitute ss over ls to obtain. So if we eliminating ss over ls, we can obtain this equation y0 over y2 minus 1. Should try this as an exercise. Y1 over y2 to the power 1 over n, y1 over y2 minus 1. So let us box this equation. From here we can solve y1. Alright, so solve y1 from this equation. In general, y0 inlet concentration of the liquid to be treated and the exit concentration y2 are known. So from y0, y2 we can solve for y1. Once we know y1, we can solve for x1, which is nothing but y1 over m to the power 1 over n. And once we know x1, we can go back to the equation 1 and we can solve for ss, kg per second of solid required to treat this feed. Alright, so that's the usual procedures. Of course, going back to these equations, this required some iteration here. Alright, so from the iterations one can solve y1, the intermediate concentration. So this y1 is nothing but intermediate concentration, and then from this number we get y0, y2 are known to us. We get x1. From x1 we can go back to the equation 1, and from there we can get this solvent amount. Now let's mark all these points for two-stage contactor. Say y0 we have, x1 we have. Go back to the previous schematic for two stages contactor. We have y1, x2, and then we have y2 and x3. So let's mark these points on the graph. Alright, or we can solve graphically as well. So we start from here. We have this y versus x. Let's say this is the equilibrium diagram. What is given to us? So we have stage 1, stage 2, incoming stream y0, y1 and y2, and we have ss. So we have x0, let's say x0 is 0, we have x2, we have x1, and here we have ls. So let's see, this is y0. So y0 is here. Let's mark these points first, and y2 is given to us, x0 is given to us. So starting from y2 and x0, let's say this is y2, and this coordinate here is x0, which is 0. Now we know this is y0 here, much larger than y2, so this concentration is known to us. But notice here that we do not know the flow rate, this ss here. In other words, the slope of the operating line, which is ss over ls minus a negative slope for countercurrent stage processes, we do not know the amount of ss. In other words, this problem very similar to the previous method which we had, which we tried to solve analytically. This requires iterations. In general, suppose you have this countercurrent, we have this slope here, gs. So we have ss over ls. All right. So if you have ss over, we know the slope, we can draw this line. But in general, we do not know what is the amount of solvent. So one has to do some iterations. Say start with y2, and y2 is in equilibrium with x2. So y2 is in equilibrium with x2 here. So this would be the stage 1. Knowing x2, we can find out what is y1 from the operating line. So this is y1, and this would be stage 1. So we have the stage 1 here. All right. Once we know y1, then y1 and x1, they are in equilibrium. So we have this x1 here, alright, and once we have x1, then from this operating line we should get this y0. So look at this, if we don't have a correct estimate for slope here or the amount of solvent SS, then we get some values which is smaller than this. That means one will have to adjust the values of slope to obtain exactly y0. Alright, so in that case, going back to this slope, one will have to adjust the slope here. So it requires some iterations to obtain this two stages process, where we have brought down the concentration of feed from y0 to y2, and the solid phase concentration has increased from x0 to x1 by two stages, stage 1 here and we have stage 2 here. Now there is another method of, or another approach here. Suppose we have, let's redraw this graph here for two stage countercurrent process. So here we have y0, we have y2, and we know the amount of solvent here. So we have, from the slope we get x1, this is SS over LS, and here we have this y1, and from the operating line we have this x2. So this is x0 equal to 0. We said that we have stage 1, so here we have this is stage 1, let's say this is stage 1, and we have this is stage 2. Now recall, we said that in the previous class that this countercurrent stage processes can also be considered as series 2 cross current stages here. In other words, look at this, y0 and x2, they are brought in contact. So let's put it y0 and x2 like this. Schematically we write like this. We have two output streams, y1 and x1, which is in equilibrium. So now we have y1 and we have this x1. Now this y1 goes to the second stage and comes in contact with x0. So now we are representing the same stage processes by cross current. Alright, so this y1 come to this x2, and now we have two streams leaving y2 and x2. But notice this x2 goes back to the first stage. So that means this is stage, we can write like this. In other words, this two stage countercurrent process is equivalent to two stage cross current processes, where this stream x2 is brought back to the first stage as incoming stream. In other words, from this graph one can also do the same analysis, assuming that it's a cross current process. So starting from say y2, y0, x2, so this is y0 and x2, this coordinate here. Now you take a negative slope for cross current. For counter current we have SS over LS, and for this cross current, if you recall from a stoichiometry balance or a species balance, now you can draw the slope with the line as SS over LS, except this is now negative. And similarly here we can have this x2, and we can draw the second slope of the curve as SS over LS. The amount of solvent is the same as the previous case. In other words, these are the first stage, this is the second stage. Now we have put them as a cross current. Two methods are same and they must give you the same result. Starting from x0, now we start from the first stage, we bring down to this level here y1. Now we bring in contact with this x2, y1 here, we bring in the contacts with now x2 here to bring back to the second stage where we have this y2 and x2. Okay, so y1 and x2 again they are in contact here to bring back this concentration level at y2. Alright, so one can also do this analysis, or you have different interpretations, whether you have a counter current method or you have a cross current methods. Okay, now we take an example of one stage and two stage adsorption process. Alright, so what we have here in this example, we have water which contains some dye or color, okay, and then bring in contact with charcoal or carbon. Alright, so the equilibrium data, the way it is given is kg carbon, so how much amount of solid is required per kg of solutions. So the way this experiment was done, you start with certain color. Now the color will also have certain units, say kg some units. That means one has measured this color, say by spectrophotometer, UV vis. So it has certain units. Okay, so kg units per kg of solutions. And for to remove this color, we have brought this carbon here. So how much amount of carbon is required per kg of solutions? Okay, so the data is given like this. To begin with, this solutions has 9.6 units of color. Okay, so this is the first data. You have starting with water, which contains 9.6 amount of color. Now in this you add 0.001 kg of carbon. So your basis is, let's say we have the feed and we start with 1000 kg of solutions. Okay, so per kg of solution has 9.6 units, and then you bring in contact with 0.001 amount of carbon per kg of solutions. Now because of adsorptions, the color is now reduced to 8.6. You add some more, you have now 0.4 at equilibrium. Now the color unit is 6.3. Similarly, you have this data here: 0.008, 4.3, 0.02, 1.7, here 0.04, and here you have 0.7. Okay, so the question is, starting with 9.6, we want to, so y0 is, let's say, 9.6. We want to reduce to y1 equal to 0.96, and we have single stage and we have two stages. So here stages are given, and we have been asked to find out how much amount of solvent is required. So this is a very previous case, right? Whenever you have been given the stages and you are asked to find out solvent, the solution will require iterations. This is in general, you must have noticed in the earlier class also. But if the amount of solvent is given, then how many stages are required, then it's a straightforward problem. So here we will see that graphically or analytically how we calculate the amount of solvent. Okay, so the first thing here is that we must convert this unit the way we have done earlier. So we have this y and x, where we write y as kg of, say, adsorbate. So adsorbate is color here, either kg or we can have unit, some unit. So here we have color, so adsorbate per amount of solutions. So that's your y, and here we have kg adsorbate, which is again your, or unit, certain units of color per amount of carbon. So this is solid phase x, and y is your liquid phase. Now from this we are supposed to convert into this. All right, so notice this is 9.6, 8.6, 6.3, which is same as this. We have 9.6, 8.6, 6.3, 4.3, 1.7, 0.7. So the first, of course, we leave it like this. So now 9.6 has become 8.6 after we added 0.001 kg of carbon. That means the amount adsorbed is 9.6 minus 8.6 divided by 0.001. So this would be the first data point which is in equilibrium with this liquid phase. Similarly, we have 6.3 here. So starting with 9.6 minus 6.3, we brought in contact with 0.004 amount of kg, we have this number here, and similarly, etc. All these numbers, if you calculate, you have 1000, 825, 663, 395, and you have 223. All right, so now we have y versus x diagram, which we can plot, and since the variation is a lot, it's not a bad idea to plot on log scale. All right, so if you plot on log scale 100, and here we have 1000, 0.6 for y, the lowest units, and here we have 10. So essentially, if you plot this data, should and fit this friendly isotherms. So if you take a slope here, a log here, log y equal to log m plus n of log x. So on log plot, this line will be a straight line. So essentially, you have the data points which are fitted by the friendly isotherms. From this slope an intercept one can calculate. You will see that n power is 1.66 and m is 8.9 10 to the power minus 5. So now you have an isotherms which you can write as y star to represent equilibrium, 8.9 10 to the power minus 5, x 1.66. So you have kg of adjorbed bit, which is color here, per kg of solutions. So of course you are writing your kg, but this is nothing but some units of color. Similarly here you have this x, which is again some kg, or you have units of adjorbed bit per kg of carbon. And also notice this, that when we write solutions, and here this should have been a small y, alright. Essentially this nomenclature capital A, Y and capital X we use for solute free basis, but here it's a very small amount of solutes, so approximately y has been approximated as capital Y, X as capital X. Alright, one can still work on a small y and a small x, but without much of improvement in the accuracies. So whenever we have the dilute solutions, we have seen in the case of absorption also that in general one can still use capital Y and capital X and get a straight line for both equilibrium as well as the operating line. So after this we get N, M, we have the isotherms, Friedrich isotherms. Now we can start making the species balance, or we can draw the operating line. So let's say that we have single stage. Alright, so it's a very straightforward problem now. We have stage 1. We have the solutions, say LS, either you put it kg per second or just kg. This contains color, which is 9.6. Bring in contact with certain amount of solid carbon, which is x0 here. Alright, x0 is 0. Let's say pure carbon we have, pure charcoal. And after treatment we have SS, and this unit is x1, and the solvent reduced, this flow rate is LS, but the concentration is now y1 equal to 0.96 kg or unit of color per amount of solvent. Of course solvent or solution, assuming that it's a dilute system. Okay, and we notice that x1 is an equilibrium with y1, so it's given by operating by the equilibrium curve, and we just write down a simple material balance here. Species balance, you have x1 equal to ls y0 minus y1. SS we have to find out. X0 is 0 here. LS is given 1000 kg per 1000 kg of solution or solvent we have. Y0 is given to us, y1 is given to us. We have two unknowns here, SS and x1, but you must realize that x1 is in equilibrium with y1, so we have y1 equal to m x1 to the power n Friedrich isotherms. So x1 equal to y1, which is 0.96 over 8.9 to the power 10 to the power minus 5 to this power 1 over 1.66. So that's n, and if you do these calculations you will get 260 units. So again this is x1, this is your 260 of mass, this color adsorbed in this carbon solid phase. Okay, and SS will be equal to 0.032, x0 is 0 here, into 1000, this is your 32 kg of carbon. Alright, so this calculation can also be done here, x1 minus x0, x1 we have calculated, now we know ls, y0 minus y1, we can put these equations to obtain SS equal to 32 kg of carbon. Alright, notice here that if you plot on the graph, then y1 is 0.96 here. If you read from directly from the graph, you should be able to obtain this 260. So this is x, this is y, and here without solving, all it means one can, if we have plotted the graph, we can read from the graph to obtain this values of x1 instead for y1. Alright, so more important now is the second stage. Let's say that we are using two stages countercurrent process. So now we have two stages, countercurrent. All right. You can recall we just now we said that if the stages are given and we are asked to find out how much is the amount of solvent or solid here, then it requires iteration. We have seen in the earlier slide as well. So let's see, we can solve graphically as well as we can solve mathematically. Let's plot the graph first for our understanding. So we have x, we have y, we have this equilibrium curve. All right. Now let's say it's linear. So here we have 0 to x. We can also plot on log to make it like this state linear equations here, linear line here. So let's say this is 0, this is 1000. Now here we have 10. So what is given here is two stages. Solution enters here with y0, which is given to us. Y1 is intermediate, we don't know. Y2 is given to us 0.96. X0 is known to us, pure charcoal. X1 is intermediate, stage 1, stage 2, counting from left to right, and here we have this x2. So x2 is not known to us, x1 is not known to us. LS we know 1000 kg of solutions. Solvent, the solid, we do not know. All right. So these are the three 1, 2, 3, 4 unknowns. So we would be expecting we require 4. So 4 unknowns. So we require 4 equations. Of course, we can go back and we can put down all the equations here. For example, LS y0 minus y1 first stage equal to SS x2 minus x1. Second stage LS y1 minus y2 equal to SS x0 minus x2. So these are the two material balance or species balance for two stages. But y1 here we have, sorry, this is x2 and this is x1. So y1 x1 is in equilibrium. So we have y1 equal to m x1 to the power n. Y2 and x2 are in equilibrium. So we have y2 equal to m x2 to the power n. So 4 unknowns and 4 equations. We can solve this to obtain SS as 12.8 kg of carbon is required per 1000 kg of solutions. As in comparison to what we had earlier, 32 kg of carbon for 1000 kg of solutions. So of course, two stages is much more efficient. But more important here is that when we say that we are going to solve analytically, you must realize that this is not a straightforward, it's non-linear equations. So in general, we require some type of iterations here. Because if you want to substitute y1 in terms of x1, which was this intermediate here, you go back to this x1, but SS is not known. Then you're supposed to replace y2 in terms of x2 in the second equations, divide the two equations, etc. You will get non-linear equations. You can solve maybe by iterations. So this iteration business should also appear on the graph here. Okay. So as we have seen in the earlier also, so start with say y0. So y0, and here we have y2. So these are the 2 points known to us. X0 is known to us. So we can start from here. Let's say y2, which is 0.96, and this is 0 here. So this coordinate is y2 x0. Now we know y1, incoming concentrations, which is 9.6. But we do not know the amount of the solvent. All we know there are two stages. So if we know the amount of the solvent, of course, we can draw a line curve like this. All right, which is positive slope for countercurrent. This should be equal to SS over LS. But we do not know SS. That means we require iterations. Let's say we have made a good guess that all it means for this y1, oh sorry, this is y0 here. For this y0, this concentration must be x1. Okay, so we do not know, of course. So all we know there are two stages. So starting from y2 x0, now let's say y2 is in equilibrium. This is here we have y2 x0. So y2 is in equilibrium with x2. So we have this x2. x2 extend to the operating line, we get y1, and y1 x1 they are in equilibrium, we will get this x1 exactly here. So this is stage 1, and this is stage 2. Alright, or if we can't do the counting from here, this is stage 1, this is stage 2. So notice that if you have made a good guess, then of course this will reach exactly at x1, and this x1 will be shown whatever we have got from the previous 260, etc. we should obtain from here. Okay, but notice here this x1, if you do not know the slope, then it might require iteration. That means one has to go like this, okay, and then see whether we get the correct values of y0 or x1. All here we know is only the x0, so this point is not known to us. So when we start from here, stages are not given to us. So notice that if we suppose we make a first case like this, then we have this operating line. Now x2 is moved here, let's say x2 prime, and this x2 prime and y1, now given this, we will get some other x1 prime here. Alright, so this required some iterations. We may not be able to achieve the same y0 what we have obtained here. Maybe will be first iterations we will have y0 prime here. One has to adjust the slope again back to this to obtain the correct values at exactly at 2 stages where we have this x1 here. If we put all these numbers here, x1, x2, etc., this x1 will be 675. Okay, so from the slope here also one can obtain the values of ss, which is nothing but ls y0 minus y2 over x1 minus x0. So that's a triangle you have taken. ls is 1000, y0 is 9.6 minus 0.96 over 675 minus 0. Alright, this will give us 12.8 kg of carbon per 1000 kg of solutions. So again we want to make a note here that if the stages are not given to us, then it requires iterations starting from y and x. First you are supposed to do is take the equilibrium curve and mark this what we know. So y0 is known here. All we know is y1 and x0, which is 0. That's it. All intermediate values y1, x2 after the first stage, they are unknown to us. All we know, y1 is in equilibrium with x1, and y2, which is the exit concentrations, which we have exit concentration here at, sorry, this is y2, this is in equilibrium with x2. So first stage, if we draw starting from here, say we get x2. Now we do not know the operating line because we do not know the slope here, which is ss over ls. Let's say arbitrarily if we make a slope like this. So if this is the correct slope, then from this x2 we should obtain this y1. So this is stage 1 stage here. Alright, so this would be starting from the end, so this is the second stage. Now this y1 is in equilibrium, so we have this x1. Alright, but this x1 now should give us y0. So if we extend this, now this should give us y0, which we don't have, y0 prime. So look at the error here. Alright, or it means we are supposed to now increase the flow rate. So gs by ls, the slope is ss by ls. So now we increase the amount of gs. So slope if increase, and let's say if we increase like this, now restart the calculations from here. y2, x2, now you go to this different levels of x2, now you go to this level here, now we have y1. Come back to this equilibrium, take this extend here, now again if you extend, this has just exceeded y0. So that means somewhere in between we require this slope. Alright, so this requires iterations. Either you do graphically or if you do it analytically. We have seen there is a non-linearity in the equations. However, if the number of stages are given, if you know there are 2 stages, how much amount of solvent is required, sorry, other way around, if this amount of solvent is required, then if this amount of solvent is given, then we can draw this line and then we can find out how many stages are required to achieve this y2. Alright, so this was the example we have taken for single stage, and for the double stage, second stage, the adsorptions. Okay, again we said in the previous lecture also that one can solve graphically or one can solve analytically. Analytically, when you solve, you require some iterations. If you solve graphically, then one has to adjust the slope of the graph. So you have the similar type of iterations. Okay. Next lecture, when we meet, we will take some more example on the search options, either for a single stage or multi-stage, countercurrent or cross current, before we start this backbed column, which is a continuous backbed. So we had two cases. One is a stagewise, and one is a continuous column backbed.